loud. Okay. Okay. So today I will speak about the electromagnetic transitions. Okay. And let's say, just to remind you, obviously in 1900, there was the discovery of Planck of the black body radiation. Then, remember, in 1905, there was the Einstein, the photoelectric effects. Effect. Then, in 1913, Bohr developed its model for the hydrogen atom. And in 1990, Einstein introduced the two-level model. That is what I want to discuss now. Okay, so today I want to start discussing the two-level model of system due to Einstein. That is a model to describe the electromagnetic transitions. Okay, it's a sort of phenomenological model, but very interesting. And then we will continue discussing more in detail and using the second quantization formalism, the electromagnetic transitions. Just to remind you, in 1924, Heisenberg introduced the matrix mechanics. And in 1927, Schrödinger introduced its equation. And in 1927, Dirac, for the first time, introduced the second quantization of the electromagnetic field. Okay, the second quantization of the electromagnetic field. And remember, this is what we discussed in the previous lessons. Okay, the second quantization of the magnetic field. Now, the model of Einstein is also called two-level model or two-level system. assumes that you have many atoms. For instance, suppose, let's say, instead of writing many, we can write n atoms, and that for simplicity, we are considering two n identical atoms. And we are considering two specific quantum levels of these atoms. As you know, as shown theoretically by Bohr and by others, and also experimentalists, by many experimentalists, the energy of bound states of electrons in atoms is quantized. And Einstein considered three possible mechanisms of electromagnetic transition. One is the spontaneous emission. Okay. In the spontaneous emission, what happens? Well, there are two energy levels, and now I draw them. I draw here, I plot here a solid horizontal line that corresponds to an energy levels with energy, say, capital E sub index B, and another energy level with lower energy, capital E sub index A. And maybe just to be a bit more quantum, we can also denote this state with cat B, and we can denote this state with cat A. Okay? Now, in the spontaneous emission, initially there is an electron in the higher energy level, and spontaneously, so it means without any forces that is acting on the electron jumps to the lower energy level, but because the system, the energy is diminishing, the energy of the electron is diminishing, to conserve the energy, something happens, and what happens? It happens that maybe one photon is emitted. Okay, so in this spontaneous emission, simply the electron goes from a higher energy level to a lower energy level, emitting a photon. But the energy of this photon, as you know, can be written as h times nu, or h bar times omega, as you prefer. Maybe it's better to write h bar times omega, and this is the frequency of the photon, and omega, but this must be equal obviously to the energy difference, capital E sub index B minus capital E sub index A. This is the spontaneous emission. But there are other two mechanisms of emission. Well, one is the so-called stimulated emission. you hear me? Is everything clear?
Yes.
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 Very good. So in this stimulated emission, again, you have two possible energy levels. Cat B, cat A, with energies capital E sub units B, capital E sub units A. Again, the electron is in the highest energy level, but in this case, one photon arrives close to the electron. Actually, this photon simply interact with the system, but it remains there. So the energy of this photon is conserved. But due to the interaction between the photon and the electron is stimulated to decay to a lowest energy level, emitting a photon. This phenomenon happens if the energy of the photon that is stimulating the emission is exactly equal to the energy difference of the two energy levels. Well, exactly or very close, let's say. So if the energy of the photon, the stimulating photon, is in resonance, so very close to the energy difference of the two energy levels, then the electron is stimulated to go down, and the system emits another photon, and also the other photon has the same energy of the stimulating one, the same energy of the stimulating one. Moreover, it has also the same wave vector. This is quite important because it means that the direction of emission of the second photon is the same of the first one. Moreover, the frequency of the two photons is the same. And this is indeed the mechanism that is the main mechanism that is was used and that is used now to produce laser light. Okay, the stimulated emission. In the case of the spontaneous emission, this photon is emitted, but the direction of emission is random. So if you have many atoms that are simply doing a spontaneous emission or radiation, the photons have the same frequency if they start from, if the energy gap is the same, but the direction of the photon is completely different, is random. So it is an incoherent emission from this point of view. While this emission, the one of the stimulated phenomenon, is coherent. Okay, that is important. There is a third mechanism that is called simply absorption. In this case, again, you have two energy levels. Again, one energy level can be indicated as capital E sub units B, and the other capital E sub units A. And the states can be indicated as cat B and cat A. But in this case, at the beginning, the electron is in the lower energy level, but it arrives a photon. And with energy h bar times omega. If the energy of the photon is in resonance with this energy difference of the levels, so if again h bar times omega is equal to capital E sub index B minus capital E sub index A, the photon can be absorbed, so it disappears, and the energy, however, is conserved, and the electrons move up here to the higher energy level. Okay? So you see, there are three main mechanisms, and these mechanisms were considered exactly by Einstein. Let's see how. So the idea for Einstein was the following. Okay, we have n identical atoms, and these n identical atoms have these two energy levels, and there are transitions from these two energy levels. Obviously, it's an approximation because in general there are many energy levels in an atom, but he is considering a simplified model. Okay? So in this simplified model, you can say that your n atoms can be divided in two groups, namely the number of atoms that are in the lowest energy level, that are in the level labeled A, plus the number of atoms which are in the higher energy level, the one labeled by B. Okay? Because we have two levels more. Okay? In general, the number of atoms that have the electron in the lowest, the lower energy level depends on time, because during time evolution there could be a transition of electrons from one level to the other, and obviously also this n stability B in general is a function of time. However, if the total number of atoms is fixed, this capital N is instead time independent. Okay? And this means that if we formally do the derivative of capital N with respect to time, this must be 0. Okay? This must be 0. But because of the previous equation, clearly this implies that the number of atoms that are in the level A must be equal to minus the number of atoms that are in the level B. Okay? Do you have questions? Okay, so I can continue. Now Einstein saying that we can consider the time derivative of the number of atoms in the level, for instance, A. Okay. That means it is a sort of rate of increase or decrease of this number of atoms. Okay. Obviously, this will be equal to minus the derivative with respect to time of NB. But now, Einstein considers the three possible mechanisms: the spontaneous emission, the stimulated emission, and the absorption. And so Einstein says at that time and says also now if it will be available for a Zoom meeting. This derivative should be proportional to some coefficient capital A that will be somehow a coefficient related to the spontaneous emission, is the coefficient of the spontaneous emission. And this is time independent. But in general, it depends this coefficient on the system you are considering, or the atom you are considering, and in particular, it will depend on the two energy levels that you are considering. And for this reason, I can put also here sub-indices BA. I write before B because it's a spontaneous emission, so of course I write the state of where the electron starts, and then the state of where the electron arrives. Okay? And the idea is that this rate is proportional to this coefficient. So this is larger, this is larger. But it should also depend on the number of atoms that you have in the higher energy level. So this should be also proportional to times and sub-index B of T. Okay, and this is the first contribution due to the spontaneous emission. Obviously, Einstein was not I must say, well, historically, this is an important remark. Historically, Einstein was not able to calculate this coefficient, and somehow he created this two-level model just to derive a formula for this coefficient capital A of the spontaneous emission, as you will see. But there are three mechanisms possible. Obviously, with this mechanism, this object is increasing because we suppose that this A is positive. But there is another mechanism that can increase the number of atoms that are in the lower level. That is the stimulated emission. So for this stimulated emission, Einstein used a different coefficient, capital B. And again, he assumed that this stimulated emission is proportional to the number of atoms that are in the higher level, NB. So NB, this is the stimulated emission. Obviously, this coefficient in general depends on the atoms you are considering, and in particular on the energy levels you are considering. So it's better also here to put sub-indices B to B. But as we have seen, in the stimulated emission, there is a stimulus. And the stimulus is related to the photons that are stimulating. Here I am considering one photon, but in general there can be a lot of photons that can stimulate the emission. And Einstein took into account this effect by multiplying these quantities also by this rho of omega, where this rho of omega is the energy density per frequency of the electromagnetic field that is stimulating the transition. So this I can write it lower. Maybe I can write it here. This rho of omega is the energy density per unit of frequency, per frequency. In practice, you can say that if capital E is the total energy of the electromagnetic field, and if you divide it by the volume, this rho of omega is such that the integral with respect to omega, with omega that goes from 0 to plus infinity, of rho of omega gives exactly the energy per divided by the volume of the electromagnetic field. Okay. So this rho of omega dimensionally is joule divided by cubic meters and also divided by hertz. Okay. Is it clear?
Yes.
But there is a third term, the one related to the absorption. So maybe what I can do here is to simply rewrite the expression. Maybe here, maybe I can simply, well, maybe I can. The expression continues here. So this first term, second term, there is a third term, but the third term has a minus. Okay, because this term, the absorption is diminishing the atoms that the atoms that are in the level A, because the electrons of these atoms are going to the level B. Okay, due to the absorption. And so, and here there should be, well, strictly speaking, there should be a third coefficient C. This is instead proportional to the number of atoms that are in the level A. But again, this is proportional also to the this rho of omega. Okay. And in general, this coefficient C, that is the coefficient of the absorption, is again dependent on the two level energy levels we have considered. So it will depend in this case on A and B. I write before A because the starting energy level is A, and the right then B because the final energy level is B. this transition. Okay. So there are these three mechanisms. Spontaneous emission, stimulated emission, and absorption. Well, strictly, I must add that for historical reason, this coefficient C sub-index AB is usually denoted as capital B. So the same symbol that appears here with capital B with sub-index A. This is a bit, so to say, strange, but this in the original paper of Einstein, there are the coefficient A, there is the coefficient A, and there are two coefficients B. The coefficient B is sub-index BA, and the coefficient capital B is sub-index A. Okay, but this means a third coefficient in practice. Okay. Probably Einstein used the same symbol, capital B, because in both cases there is the presence of stimulating photons. And also because at the end of the calculations, we will see that the coefficient B with sub-index BA is equal to the coefficient B with sub-indices AB. But this is the final result, actually. We have to prove it. Okay. So, but for sure, there is this equation. It's a dynamic. Obviously, there are two equations. There is this equation and the other equation. But you know that the other equation is D and B over DE is equal to minus D and A over D. So the two equations are coupled. If you solve this, you can also solve the other. Okay. The dynamical variables here are the number of atoms in the individual states. And in general, we have to solve this equation. I must add that this is the general formula, but here I was cheating a bit because the omega that appears here must be the correct omega, namely the one that induces the stimulated emission and the one that induces the absorption. And as we have seen previously, the correct omega is the one that is in resonance with the two energy levels. In practice, the correct omega is this omega, let's call it omega BA, and this is by definition the energy of the higher level A sub-index B minus the energy of the lower level capital A sub-index A divided by each part. This is also called the Bohr frequency. If the photon has this frequency, there is the stimulus. Okay, but the stimulus is very effective, so the omega that should be used here is omega BA, and also here. Okay, this is also called Bohr frequency. It is the energy, the frequency of the photon, but to have the stimulus, an efficient stimulus, it must be in resonance with the energy of the atoms, so should be equal to this energy difference divided by each one. Okay, this is quite important. Now, the reasoning of Einstein proceeds then in this way. He assumes that for some reason, the system, and the system is the gas of non-interacting atoms with these two energy levels, coupled to the electromagnetic field. This system somehow reaches equilibrium. Actually, two kinds of equilibrium. Dynamical equilibrium and dynamical equilibrium simply means that the time dependence disappears. So in practice means that the derivative with respect to time also of n sub index A is zero. This is the condition for dynamical equilibrium. And obviously, this implies that also the n sub index B divided by dt must be zero. Okay? This is the dynamical equilibrium. So the dynamical variables do not depend on time. But then, in addition, if you want, Einstein assumed also the thermal equilibrium. And this means that not only the system is a dynamical equilibrium, but in addition, these dynamical variables, of course, are no more dynamical because there is no time dependence. And second, these variables N, A, and B are thermally distributed according to the Maxwell-Boltzmann distribution. So if we assume that N B must be, say, proportional to E2 minus beta, where beta, this beta is as usual 1 divided with Boltzmann constant times the absolute temperature. And E2 minus beta times at the exponent the energy capital E sub index. Okay. And a similar relation also for N sub index A. So in practice, assuming that the constant of proportionality is the same, so the idea of Einstein was that NB divided by N sub index A must be equal to this object divided by this one, E2 minus beta, capital E sub index A. Okay? Or, if you want, this can be also rewritten as E2 minus beta, open the round bracket, capital E sub index B minus capital E sub index A. Okay, so this is an important assumption, thermal equilibrium, where the distributions of the atoms in the two energy levels follows this law. So if you want, if the energy is higher, then the number of atoms, that have that energy is lower, okay, according to the Maxwell-Boltzmann distribution. But in the problem, there is not only the number of atoms, but also the electromagnetic field. And the idea is that the electromagnetic field must be at thermal equilibrium with the same temperature of the atoms. And so, thermal equilibrium implies also that our rho of omega, that remember is the energy density per frequency of the electromagnetic field, this object must be the one at thermal equilibrium. But in our previous lesson, unfortunately done only with pre-recorded videos, I have shown that this rho of omega can be written normally as the quantum Hamiltonian of the electromagnetic field to the F divided by the volume doing the thermal energy. And we have calculated this object. And sorry. We have seen that this quantity is such that if we have the this object, capital H to the F divided by the volume and thermal energy, this can be written as I wrote also there, as the integral from 0 plus infinity of rho of omega d omega. And this rho of omega has a very specific formula, and that is the in practice the norm. Do you know what is this formula? What is the formula of rho of omega? It is the Planck law of the black body radiation. So it will be for sure, there should be here the denominator E2 beta, then there should be h bar omega minus 1. This is for sure. Then I am quite sure there should be omega to power 3. And there should be some coefficients here, but I don't remember the coefficients, so I must take my notes, and in the notes there is the formula where there is also the coefficient. Yes, so there is in front there is h bar, and then there is a denominator pi square. And c, that is the speed of light, q. Okay. We are supposing, and where is the temperature? The temperature is here, because beta is the inverse of the temperature. So this is the expression of thermal equilibrium. And if you want, because we are working with omega equal to omega dA, so here dA, so there will be dA here. And also the here. Okay. Okay. Well, maybe I can try to conclude this part before the break. Now we have thermal equilibrium, and we can now consider again the general formula, the dynamic formula, assuming equilibrium and thermal equilibrium. Okay, assuming equilibrium, this object must be 0. Assuming equilibrium, the time dependence is 0. And I have this expression. Moreover, well, now here using exactly the Einstein notation, instead of using capital C, I use capital D, D. Okay. Then now the idea is to write rho in terms of what remains. So practice, I can do the following. I can do the following. I can write rho of omega something is B times open the bracket capital B something is BA times n something is B. It is this expression minus this one capital B something is B times n something is B. This object must be equal to minus capital A sub B is B times NB. Okay. Is it correct? Okay. I will continue. This means that this rho function of omega B is equal to capital A sub B is B times n capital S B divided by, I have to revert this expression, so we have to write n B A B and A minus capital B, something this is B and okay, now I have this formula. I simply divide everything by capital A something this B. And if I divide by capital N something is B, sorry, if I divide by it, here I get this one, and here I get this divided by this, that is the same quantity, so it gives 1, I get this expression. Okay? Now, I write capital A sub A is B divided by, now I have this B sub A is B times, but you see this ratio NA divided by NB is exactly the inverse of this one, that is instead NB divided by NA. So the result must be E2 beta E sub index B minus E sub index minus capital B sub index B. Okay, this expression. Now, and B capital E sub index B minus capital E sub index A is nothing else than H bar omega sub index BA. Okay. Now we can compare this expression, this rho of omega BA equal to this object, with this expression here. See, so this should be equal to, say, I will carry on to H bar divided by pi squared C cube omega sub index BA cube divided by E to beta H bar omega BA minus 1. So you see, simply by comparison, comparing this expression to this one deduces that to get something fully consistent, I must say that I'm not fully sure that it's the only solution, but for sure is a solution. What solution is BAB equal to cap B BA. Okay, and moreover, A subindex BA divided by B subindex say BA, because they are equal, must be given by this expression here. So must be H bar omega subindex BA cube divided by pi squared C cube. Okay. So the conclusion of this reasoning is that the two coefficients related to the stimulus, namely related to the stimulated emission and to the absorption, must be equal. And instead, the coefficient of the spontaneous emission, this capital A, is somehow proportional to the coefficient of the stimulated emission, but with a constant of proportionality that is exactly being given by this expression, and in particular, it depends on the frequency Q. Okay. Einstein did this reasoning because, as I said previously, he was unable to calculate this coefficient capital A, but instead he was able to calculate the coefficient capital B. And in this way, knowing capital B, you can immediately find capital A. Okay. Now, after the break, we will see how we can calculate explicitly this capital A using the second quantization formalism of Dirac. However, remember that the second quantization formalism of Dirac was introduced in 1927, while the two-system model of Einstein is of 1990, so previously. And also Einstein, as I repeat, was able to calculate the coefficient B, and from it was able to deduce the coefficient A. So I can stop here. Do you have questions, comments? Okay, so maybe I can. Let's say, for instance, what I can do, I can stop the call.